Hello and welcome back to Calculus 3, section 16.5 on triple integrals in cylindrical and spherical coordinates. So these are the new coordinate systems for 3D, which we have not discussed so far. Both of them are built on top of the polar coordinates. Polar coordinates are 2D. Oh, great. Pen is not working. So polar coordinates are 2D. And I'm using my fingers, it looks like. Huh? Well, it's eventually going to reboot. I'm rebooting it. So let's see. It will take some seconds. So polar coordinates are r comma theta, and it's a 2D concept. Now, in order for the polar coordinates to work, we said that we had our good old x, y, and then to reach the point, we had radius r and angle theta. So this is what you guys learned in your Calculus 2 course. So now, on top of this, we are going to add the oh, come on. I give up. Come on, connect. So now, on top of the polar coordinates, to come up with a cylindrical coordinate, we're just going to add a z coordinate. Yes?
We decided that we would take the exam Thursday.
This Thursday?
Yes.
Okay. Understood.
Well,
thank you. It's very thoughtful.
Quizzes are going to be open, right?
Yes. Tonight.
And they're just all going to be open until the date, or they're going to be scheduled again?
Beyond the date, so one a day. Still prep.
Okay, so it's, I get it.
Yeah. So now, for cylindrical coordinates, we are going to have r comma theta comma z. And the way those work are in the cylinder. Where you have the radius r and then some angle. So this is your xy. You have some angle theta and then radius r, and then it's going to go up to some, it's going to go up to some value z. On the z-axis. Technically creating this plane over here that again has the radius r on top and the bottom and the size z over here. So cylindrical coordinates can be very, very useful, because we get to transform the integrals that we can't compute into these, and we use the polar coordinates conversion, and z equals z. That stays the same. So let's just take a look at some basic shapes. So the first basic shape is the cylinder. And that one would be r equals a, right, where you have some radius r equals a. So that's one of the basic shapes. Then we have a cylindrical shell, which is technically just like a piece of a hose or something. It's just there's a hole inside. And there are two radii, A and B. So cylindrical shell, and R is in between A and B. Now vertical half plane. Is theta equals theta 0. So you get to swing this from x-axis to some theta 0 angle. And we'll have a cone. Oh, a horizontal plane, that one is easy, but that one is not cylindrical, that's also rectangular. So if you have your standard xy, xyz, you have a plane over here, which is z equals to a. So horizontal plane. And finally cone. Z equals AR. So these are some basic shapes in cylindrical coordinates, but what we like to do is to worry about conversion. X equals r cosine theta, y equal r sine theta. That's one pair. And then r equals square root of x squared plus y squared, and theta equals inverse tangent of y over x. That's the other pair. So this one is polar into rectangular. Actually, you know what? I don't want to write them as a polar and rectangular. Let me add. I'm going to add more stuff here. I'm just going to add z equals z for both of these. So I'm going to move this down, add z equals z, and z equals z. So I can say rectangular to cylindrical. So this is cylindrical into rectangular, and over here it's rectangular into cylindrical for conversion. There we go, much better. Alright, so please don't freak out when you see the integral, because it just looks bad, but it's actually not that bad. So cylindrical triple integral in cylindrical coordinates. So we have a regular integral, triple integral dv, and that's going to be this triple integral now, which has f of r cosine theta, r sine theta, and z dz r dr d theta. I hope you remember the string for polar r dr d theta. Remember it? We are just inserting now z in the middle of that integral. Theta has limits alpha and beta. The limits for the inner one would be g of theta and h of theta. Those are the r equals, right, r equals f of theta, so r1 equals g of theta, r2 equals g h of theta. And finally, g has to be in terms of r cosine theta, r sine theta, and h, r cosine theta, r sine theta. This is one of those cool things that you can just casually leave on a napkin when you go out and just walk out. Let them figure it out. It looks terrifying, but when you consider that this is just your x and this is your y, which means this is your x and this is your y, what is this technically telling you? Right? It's just f of x, y, z, right? And then you have g of x, y, g of... So it looks bad, but it's actually not. But let's see it in action. We start with a soda can. Now, as I go to the internets to see soda can dimensions. Soda can dimensions of 12 US fluid ounces, 355 milliliters. Standard can is the height of 4.83 inch and diameter of 2.6 inch. Great. So this tells me that the radius of the can is 1.3 inch. That's what I care about. Yes, we can go and figure this out using algebra, but we're not gonna, right? We're gonna make this nice and spicy. We're going to do the volume as a triple integral, and then I'm just going to have the z, r, dr, d theta. Now, guys, this is the string that doesn't change. Right? It stays this way. It's not going to be d theta, dr, dz, or something like that. This is it. You are either setting this one up, or you're not setting anything up, right? So this is what we have. And now I just need to look at the soda can. Soda can is sitting on a desk with a z having a 0 on the bottom and 4.83 with the height of the can, which is the plane on top. So plane on the bottom is 0, plane on the top is 483. We're done there. Radius is 0, to 1.3 because it's the full object. And finally, I want the entire can, so the theta has to go from 0 to 2 pi because it has to go through the entire object, right? Because you can take the can, you can cut it in half, and if you cut the can in half vertically, you are going to have 0 to pi because you only have half. So now you integrate this, you're going to have 0, 0, 2 pi, and 1.3. When you integrate this, you get z, so it's 4.83 over here, r, d theta, and that's going to be 0 to 2 pi. When you integrate this one, it cuts it. Do I really need 4.83? How about 4.8 and make the life easier? So 4.8, because now you gotta cut that in half, so it's 2.4 r squared from 0 to 1.3. We still have d theta to deal with, and what I get, 0 to 2 pi, square 1.3, you get 1.69, so it's 1.7. So this is 2.4 times 1.7 d theta. So the whole thing is 2 pi times 2.4 times 1.7, which is equals to a number of some kind, inches cubed. So to work on a cylinder using cylindrical coordinates, right, that's the cheapest shape that you can have, hence the name, cylindrical coordinates. But you can deal with cones, you can deal with all other kinds of shapes. So let's take a look at some other shapes that we can find. And this is one cool shape. So what I have here is going to be elliptical paraboloid that is sitting on top of some kind of cone. The top equation over here is given by z equals 12 minus x squared minus y squared. And the bottom equation, the cone, z equals square root of x squared plus y squared. This is all it's given to you. You have the top shape, you have the bottom shape. Guys, how close is this to your egg? It's the only thing that it's, right? It's really there, right? So, what do I have here? Well, when I set up my integral, look, the z is this equation, and also z is this equation, so those are my bottom and the top limit for my z integral. The volume over here is the triple integral. I'm not having any function here because I'm not working on a 4D. And I have my dz, r, dr, d theta. Usually your grade withers with this r, so don't forget it. Your top integral is 12 minus x squared minus y squared. The bottom one is the square root of x squared plus y squared. Now the question is, what's What's the rest? Well, the problem is that I actually, oh, hold on. I can't have x's and y's in limits. I can only have r's and thetas. I have to convert this into 12 minus r squared and z equals r. I have to convert these things. X squared plus y squared is r squared, and then square root and square cancel, so you just get r. So z goes from r to 12 minus r squared. Those are my z limits. I have to convert everything to r and theta. Great. So now that I have that, I have one more piece of information. Well, first of all, we see that the entire thing over here is round, so I know that 0 and 2 pi are on the outer for theta, right? The only thing that I don't know is the radius. I know it starts at 0. The question is, what is the radius when this is the fattest? And that's going to be, right, looking at the domain, and your domain in this case is going to be this circle that you get in the xy plane, and you will get that when you go 12 minus r squared is equal to r. So once you solve this problem, you will get the equation for r. So I have r squared plus r minus 12 equal to 0. When I factor this, I get r plus 4 and r minus 3. One r is negative 4, throw that in garbage, and the other r is 3. That's a good one. So 0 to 3. So I need you to stare at this until it makes some sense. I'll go through the whole argument one more time. We have this shape that is paraboloid, that is sitting on top of the cone. It's exaggerated ice cream. And we have the two equations that are given to you, right? So now, your job is to write the volume integral. Because it's a volume integral, we have three integrals. There is nothing in here, because three are already, do you have three dimensions? Sure, 1, 2, 3. We said that d theta is not a dimension. So now, the first order of business is you have to put the z r dr theta, and that's the string that stays the same every time for cylindrical coordinates. You'll have the same thing happen for spherical coordinates as well. And now, you go and you say, all right, so what's the top z? That goes in the upper limit. What's the bottom z goes in the lower limit, but you have to convert formulas into r theta because they all have to be r's. And then I have my z. It's always the top and the bottom, so top and the bottom. Z is done. The object is a full object, right? That's why it's 0 to 2 pi. The only thing that is left for me to worry about is the radius that goes, in this case, 0 to 3. And you get that when you set the two shapes equal to each other. What you get is the trace line where they meet. And the trace line is where the object is the fattest, which would actually cast a shadow on the domain. And in this case, was a circle of the radius 3. So, circle of radius 3, right? You have 0 to 3. Now, I want to ask you, what if I had a hole through this object that was of radius 1? Where would that go?
Change the radius, or the limits of integration for the radius from 1 to 3.
Yes, perfect. So if there was a tube through this, let's say this was a bead for a necklace or something, right? Then there will be a tube through the middle, and if the radius of that one is 1, then goes 1 to 3 on radius. So maybe you want to write that as notes, right? if there is a 2, radius 1, then the r limits are 1 to 3. Because your integral is supposed to be only covering the parts which contain material that we are concerned with. Let's go to homework. Pick up another shape. Here's problem 30.
And this one.
Problem 30 has this shape like this.
The first quiz. The first quiz.
So this is all you get. That's it. Well, we want the full object, right? So we know 0 to 2 pi immediately. And now we have to figure out the rest. So do we all agree that this over here is the top of the object? Do we? Yes or no?
Yeah.
Yeah. What's its equation? Of the top. Yeah. Nope.
Just z equals 25.
Z equals 25. Good. It's a horizontal, flat plane, just like a surface of your desk. The surface of each one of your desks is z equals 3, right? It's a flat surface. It should extend infinitely in x and y directions, so there are no x and y in that equation. The full surface of your desk is fully explained by z equals to 3. So z equals 25 would be the height, which immediately gives me to work on domain as x squared plus y squared equals 25. Great. Radius is 5. We convert x squared plus y squared into r, and I think we're in good shape. We can write the volume integral right now. We have the z, r, the theta. So the z goes from the bottom, which is r, to the top, which is 25. A radius is from 0 to 5. And I want the full shape, full circle, right? 0 to 2 pi.
X squared plus y squared r squared.
What happened?
Yeah, isn't x squared plus y squared equal to r squared? They both turn into r squared.
Oh, yes, you are right. Yes, r squared. Thank you. Yes, r squared. You can integrate this quickly. This is going to be 25 minus r squared, which is 25r minus r cubed over 3. That's going to be 125 minus 125 over 3. That's going to be 2 times 125 over 3 times 2 pi cancels the 2, so 4 pi times 125 over 3. That's it. That's it. Integrating this will not be a problem for any one of you. The next problem, however, a problem, okay? So this is what the question says. Integrate integral -3 to 3, integral 0 to square root of 9 minus x squared, integral 0 to 2 of 1 over 1 plus x squared plus y squared dz dy d theta. dz dy dx. Oops. There we go. That's it. That's all you got. It says integrate. Now on the exam, I usually write in a parenthesis somehow. You can't integrate this, right? Because when you do the integral dz, you get the whole fraction times dz, so it just picks up a 2. And then when you want to integrate in respect, it's just a holy nightmare. I'm going to plug in the square root then. So what do you propose to do? Can we fix this situation? Can we make this nicer?
Switch it to polar coordinates.
Cylindrical.
Yeah, that one.
That one. But what is the shape? How do I know what the limits are going to be? What am I working with over here? So now the skill is to convert these limits into a picture and then write the cylindrical integral looking at the picture you have. So let's go. From this integral, now this is crucial, guys. You have to understand this because the spherical coordinates is worse. This one over here tells me z1 equals 0, z2 equal 2. This is my bottom, right, and top. These are both planes. That just tells me that it's a flat bottom, flat top. All right? So these two tell me, actually tell me this way. Flat bottom and flat top. Great. So at least I know that much. Then I go to the next one over here, the blue one. And the blue says that y is equal to the square root of 9 minus x squared. Hey, I know that's a circle. That's a circle, x squared plus y squared equal 9. That's a radius 3. Awesome. But then I also see that the bottom is y equals 0. So if I am to draw this circle in the xy plane, I need to go from -3 to +3. Well, that's cool because I know radius is 3, so that all fits. But we know that this part, that part is the positive, and the 0 is here. Can we all stare and get that part? So actually, what do I have? I have a soda can cylinder that is vertically cut in half. So if I want to draw this, I would draw something like this. It's a half a can. And I have my axes. And please note the way these axes are here. I have flat part on x-axis and then y-axis poking out. So now as I'm setting up the volume integral, it's going to be a triple integral, again, dz r dr d theta. Z is clearly 0 to 2. It's a flat top, flat bottom, so this is a 2. That's a 0 on the bottom. Radius is 0 to 3. And this time, if you look at the angle is 0 to pi, not to 2 pi. It's to pi. Now, what has to change in the original problem so I can have 0 to 2 pi? What has to change in the original problem in order for me to have, yes, 0 to 2 pi?
dy limits of integral have to be negative that root.
Excellent.
That root.
Yes. dy integral would have to have a negative square root of 9 minus x squared in order for it, because that would include the bottom part as well. Remember that the bottom part is negative square root equation, the top part is positive square root equation. We only have positive, we don't have negative, so that's why it went from 0 to this one. Yes?
How did you get the orientation of the half circle? Is it that y equals root equation?
Yes.
Okay.
I don't have time to teach spherical coordinates tonight, so we're just going to convert another. We're just going to convert another one of these. This skill is something that is cool to have. This is a modified problem, so I'm not going to give the number. I'll just say convert and give you the triple integral to mo over. So it's going to be from negative 4 to 0, and then negative square root of 16 minus x squared to 0, and the square root of x squared plus y squared to 4, z dy dx. It's a modified problem. They have a little bit different limits, but that's okay. So try to come up with cylindrical equivalent. You have 18 seconds, no pressure. Okay, what do we have? That's the important one, right? It says y equals negative square root of 16 minus x squared. So what's that? That's x squared plus y squared equals 16. It's a circle of radius 4. Now, how much of this circle do I get to keep? Do I get to keep a whole thing? No. I know this is a negative 4 over here. So negative 4 to 0. I definitely get to keep something on the left-hand side. Right side is out. Because there is no 4 on the top. Negative 4 to 4. It's negative 4 to 0 on x. And now, do I get to keep upper part, bottom part, or both?
Just the bottom part.
Just the bottom part, because the top is 0 and the bottom is the negative square root. So this is the 0 and this is negative square root.
How did you rule out the fourth quadrant again?
No, the fourth quadrant is in.
Oh, it is. Okay.
Oh no, sorry, not the fourth quadrant. The third quadrant is in. The fourth quadrant is ruled out because of this 0 here. It's not going to 4.
Oh, okay.
X equals 0 is where it stops. So it has to stop at the y-axis. So now, to convert this integral into the triple polar integral, we have our dz, r dr d theta. Top for our z stays the same, which is 4. Bottom becomes r, because you have square root of r squared, right? And now, what are my inner integrals? What is the middle one? Yeah, but I need it in terms of, that's the r integral, so what is it?
So the 4 radius.
Yep, 0 to 4, good. And now, what is my theta?
Pi to 3 over 2, 3 pi over 2.
Excellent. Pi to 3 pi over 2. Because you have pi and then 3 pi over 2 as the end. I hope we all agree that the integral on the bottom is far easier to compute than the one on top, right? This is why these exist. In certain cases, right, when they are supposed to be used, they make a joke out of a problem. And the other one should be a living hell to compute. So they complement each other. When one is easy, other one is tough. They don't compete. Sounds good? Tomorrow we'll do the spherical coordinates, then we'll do the mass integration, and probably go and start working on the conversions as well. Bye.